Electric fields are connected with magnetic fields, and magnetic fields are connected to electric fields. We cannot see them separately. It is like we are looking to a four-dimensional field and we observe certain properties of this four-dimensional field. Einstein has developed this in his theory of special relativity together with Lorentz, who already as first noticed the transfer of electric fields into magnetic fields and magnetic fields into electric fields by the relative motion of an observer. He developed the Lorentz transformations, and when we place this with together the four-dimensional space of Minkowski, Einstein has developed together with them the theory of special relativity. And in this theory, an electric field is not separate. A magnetic field is not separate. They are both connected, only we see, depending on our relative velocity, a certain part of it. We observe it as an electric field or as a magnetic field, and when we speak about light, there's a perfect symmetry in the dividing of the fields. 50% of the field of an electromagnetic wave is electric, and 50% of the energy of an electromagnetic wave is magnetic. They are both in balance. And because both fields are connected together, we have to keep the symmetry during the calculations. So when we calculate forces in the electric field, we also have to see them back in the magnetic field. And every operator acting on an electric field also has to operate at the same time on the magnetic field. And every other operator acting on a magnetic field also has to act on the electric field. The symmetry has to be kept completely during the transport of electromagnetic energy. When we develop an equation describing the transport of electromagnetic energy, then we make use of Newton's second law of motion and transfer this equation by E is mc squared to the electromagnetic field. Then we have to take care that every actor working in the electric field also has to be operating in the magnetic field, and every actor acting in the magnetic field also has to operate in the electric field. We have to maintain the symmetry. That is fundamental. And the fundamental part of this is that whatever we do, we have to keep the symmetry in both fields. And that's one of the weak points in Maxwell's equations. In Maxwell's equations, there is no symmetry. And the symmetry is essential to describe an electromagnetic wave. Coulomb investigated the forces between electric particles. And if we calculate the force between a positive and a negative particle, in that time the idea was that an electric particle was attracted by the field of the other particle. But what is really happening is that not the particle is interacting with the field, but the field around the particle is interacting with the other field. For this reason, we cannot describe Coulomb's law by a simple equation: electric force is electric field times charge. It is normally presented like this, but this gives a wrong idea. Coulomb's law is a confusing equation because the equation suggests that fields interact with particles and that particles interact with fields, and that is completely wrong. Particles do not interact with fields, and fields do not interact with particles. Electric fields do not interact with electric particles, and electric particles never interact with electric fields. Electric fields only interact with the electric field corresponding to the particle. And that means that what the equation suggests is not the physical reality. What is really happening is that this equation presents the volume integral over the force densities per cubic meter, Newton per cubic meter, integrated over an infinite volume from two fields. One field, the electric field A, and one field corresponding to the electric charge Q. And that's what we have to calculate. So we have to transform now a similar equation, which is much more complicated because that equation is not describing anymore the charge, but it is describing the field which corresponds to this charged particle. And the total field of interaction is the volume integral of all the volume densities in Newton per cubic meter integrated over an infinite volume. To describe this interaction, we indicate this as the force AB expressing the electric field A acting on the field around the particle B. Is an interaction between two fields. Dividing by the volume, we express the force density in newtons per cubic meter, interaction between two field densities, a field density corresponding to the electric field A and a field density corresponding to the electric charged particle B.